In this video, we will talk about what a parametrization of a curve is. So here is the scenario that I want to use to motivate this. So a bug moves on the xy plane along the path in the graph below, and I'll draw that graph in a sec. How do we write a formula for its position as a function of time? Okay, so I'm going to draw some xy axes. So we're talking about the xy plane, and there's some bug, and let's say that initially at t equals 0, it starts at this point. And then the bug will start to move, so let's say the bug starts to move this way. And then by t equals 4, it reaches a point like this. So t equals 4. And then it starts to curve downwards, and maybe it makes a little loop-de-loop, and then it finishes down somewhere over here. And that's where it is at t equals 9. So t equals 9, this is the end time for the interval that we're focusing on. And t equals 0, that's the start. So we can specify the direction that the bug moved along this path with arrows. So it's going this way, moving from where it was at t equals 0 to where it was at t equals 4. I could draw some more arrows and some more arrows. So the arrows just indicate the direction that the bug is moving along the path. So one thing I want to notice about this graph is this graph fails the vertical line test. Vertical line test. It wouldn't pass the vertical line test. And when a graph doesn't pass the vertical line test, that means it is not a function. Okay, so I'm going to be a bit more precise now. When we say that this graph is not a function, we are saying that y is not a function of the variable x. So there are some situations where I could have an x value that correspond to more than one y value. And that happens in this graph. So that means that y is not a function of x. So what we can do is we can write x and y as functions of another variable, which I'm going to call t. And I'm going to have t represent the time. So the time elapsed as this bug is traveling. Okay, so t, this variable t, is called a parameter. So p is, let's write that better. This is called a parameter. All right, so what we're going to do is we're going to try to write x as some function of t. I'll call that f of t. And we'll do the same thing with y. We'll write y as g of t, some function of t. And these two equations are called a parametrization. Parametrization. Okay. In a parametrization, it describes the movement of this bug over time. And even in general, typically when we look at parametrizations, typically they're going to describe movement of something over time. Okay, so zooming out, so I could look back at my graph in this context. So the x-coordinate is being described by this function f of t. So where it is at t equals 0, this x-coordinate is f of 0. And where it is at t equals 4, that x-coordinate is f of 4. And where it is at t equals 9, that x-coordinate is f of 9. And we can similarly label the y-coordinates. So when t equals 0, that y-coordinate, that is g of 0. And when t equals 4, that y-coordinate is g of 4. And then when t equals 9, that y-coordinate is g of 9. Okay, so the x and the y-coordinates individually are functions of t, functions of time. Okay. So these parametrizations, they're going to let us handle more complicated curves than we've seen in, let's say, algebra or calculus up until this point that were typically just functions. All right, so let's do an example now. Okay, so another example with a bug, but a little bit more specific. So a bug travels along the parabola y equals x squared, t seconds after noon. The bug's x-coordinate is t. Okay, so a bug is traveling along this parabola, and this problem tells us something about, at a certain time, t seconds after noon, what the bug's x-coordinate is. It's telling us that it's t. So it's telling us that x, the x-coordinate is t, where t represents time in seconds. So if we take that x and plug it into the equation, so if we plug it into y equals x squared, we get y equals t squared. And this is a parametrization. Okay, so we know what the graph of y equals x squared looks like. We know it's a parabola that has a vertex at the origin and it's upward facing, so y equals x squared looks something like this. Okay, but when we have a parametrization for a curve, let me actually scooch the curve a little bit down. When we have a parametrization for the curve, we don't just have the curve, we have movement along the curve over time. Okay, so to get a feel for that movement, let's make a table of values. So I'll plot t, x, and y in a table of values. And I'm going to plug in some time. So let's do -2, -1, 0, 1, and 2. So when we have t equals -2, that's saying it's 2 seconds before noon. Okay, so when t equals -2, let's plug that in for the equation with an x. That gives us x equals -2. And because x is always t, whatever the t value is, the x is going to be the same. So here x is going to be -1, at 0 it's going to be 0, and it's going to be 1 here and 2 there. To get the y coordinate, we take the t value and we square it. So -2 squared, that's 4. -1 squared, that's 1. And then quickly doing the rest, this is 0, that's 1, and that's 4. Okay, so not too bad. This is what we'd expect for this parabola type equation. But now what I want to do is I want to plot these points to see where is the bug on this parabola at these certain times. So when t equals -2, maybe that's here, and that corresponds to this point on the graph when t equals -2. It corresponds to the point -2, 4. That's where the bug is on the parabola 2 seconds before noon. And then at t equals -1, that would be a point here-ish, t equals -1. And the coordinates of that point are -1, +1. So that's where the bug is at t equals -1 second. So that's 1 second before noon. Okay, then we can quickly see now that t equals 0, it's at the origin, 0, 0. At t equals 1, it would be at this point, the mirror image of where it was at -1. And t equals 2, it would be here at 2, 4. And now let's draw arrows to indicate the direction that the bug is moving in. Okay, so the bug is moving in this direction. It's sort of traveling from left to right here. So I'm indicating that with these green arrows. Okay, but this isn't the only way that we could have parametrized this bug's movement. So let's talk about some other ways to parametrize this. So next, let's suppose that we wanted to get a faster parametrization. So sometimes to abbreviate parametrization, I'm just going to write PAR''N, and that will refer to parametrization. So now let's suppose we had a bug, but it was moving faster. How could we describe that? So instead of letting x be t, let's let x be 2t. And that's going to increase the speed at which the bug travels along the x-axis, or sorry, increase the rate at which its x-coordinate changes. Okay, so the y is x squared, so that's going to be 2t squared, which is 4 times t squared. And so I know it's still going to have the same shape. We're still talking about a parabola. So we're still talking about this parabola. But what this should change, hopefully, is the speed, how fast it's going. So let's make our table t, x, and y. Just as before, I'll plug in -2, -1, 0, 1, and 2. If I plug these t values in into x first, I'll get -4, and then -2. Plugging in 0, we get 0. And then we get 2. Plugging in 2 now, we get 4. And when we plug these in to the y-coordinate, we'll end up squaring these. So we'll get 16 here, +4, 0 squared is 0, and then we'll get 4, and we'll get 16. All right, so in this case, when t equals -2, we are a lot higher up on the parabola. So when t equals -2, we are at the point -4, 16 on the parabola. And when t equals -1, so this is the point where the x-coordinate is -4. This is the point where the x-coordinate is -2. So this is -2, 4. Okay, and then when t equals 0, we are at the origin. When t equals 1, we will be over here. T equals 1. This is t equals 0. And then t equals 2, we will be up here. All right, so now let's draw arrows in the direction of our movement again. So again, we are moving from left to right in this picture, sort of across our parabola. So changing x from t to 2t sort of doubled the rate at which we traveled in the x direction here. All right, so now let's do another one of these. What if I wanted to get a parametrization in the opposite direction? I want to have you all think about this first. So pause the video for 1 minute to try this. 4, 3, 2, 1, pause the video. Pause the video for 1 minute to think about this and how you might now come up with the parametrization in the opposite direction. All right, so hopefully you've done that. Hopefully you've paused the video to try this for about a minute. Okay, so if I wanted it to go in the opposite direction, we are going to somehow need to flip where the positive t values and the negative t values are. So I can do that by letting x be -t. And then y is going to be x squared again, because that's the equation of my parabola. It was y equals x squared. So if I square -t, we get t squared, because the negative goes away when we square it. All right, so again, I know the graph is going to be a parabola shape. But let's make a table of values to see where we are at these different t values, and then draw the direction of the path. So again, t, x, and y. We've done this a few times now with this table of values, so I'll go a little bit faster. So -2, -1, 0, 1, and 2. Plugging these in for t to get x, it'll switch the sign. So we'll get 2, 1, 0, -1, and -2. Right, and then to get the y-coordinate, we square the x-coordinate. We also squared t, because we see that y equals t squared. So doing that, we'll get 4, 1, 0, 1, and 4. Okay, so when t equals -2, we're at the point 2, 4. 2, 4 would be here-ish. 2, 4. So we are now on the opposite side of the parabola, which is good. That bodes well for traveling in the opposite direction. So t equals -1 would be somewhere here, and that corresponds to the point 1, 1. Nice, and then t equals 0 again is at the bottom of this parabola, 0, 0. T equals +1 would be on this side, and then t equals +2 would be on this side. And now let's draw in the direction arrows. The direction we are traversing is now in the opposite direction along this parabola. So in terms of our goals for this video, we have done an introduction on how we describe curves with parametrizations.